Hi, welcome. In today's video, I'll show you how to find the matrix representations for the operator Sx and Sy in the Sz basis. For that, let's assume the following eigenvalue equations, where these cats along the x direction and these cats along the y direction is given by. These are the eigenvalue equations that show us what these operators Sx and Sy do when they act upon their eigenstates. So, for example, Sx acting on its eigenstates yields the eigenvalues plus or minus h bar over 2 times the respective eigenstate. Same idea applies for Sy. Now that we know the effect of these operators, what would be their faces? I mean, what would be their matrix representations? For simplicity in the Sz basis, well, I will start with Sx. Assume that it has this matrix representation A, B, C, D, which are general entries, and we need to write down the ket plus subscript x in matrix notation. As we did before, we just need to calculate these inner products. If we do, we end up with 1 over square root of 2, 1, 1. If you're not sure how to perform this calculation, you can check the previous videos where I taught how to do it. And for ket minus subscript x, this is the matrix representation for this quantum state. 1 over square root of 2, 1 minus 1. And now we can plug these matrix representations into this eigenvalue equation in order to determine what Sx is. Although here the two eigenstates are merged, I'll separate them to determine Sx. The eigenvalue equation for spin up is, and if we plug our values found previously for each one of the terms of this equation, we get, if we multiply these two matrices and these terms cancel out, we have. Then similarly for spin down, we have this following eigenvalue equation. If we plug those values back here, we find, multiplying the terms, we find this system. There are 4 unknowns and 4 equations. Then we can determine A, B, C, and D through simple algebra. Finally, with our A, B, C, and D determined, we're able to write the matrix representation for the operator Sx, which is h bar over 2, 0, 1, 1, 0. In summary, this is the matrix representation for the operator Sx in the Sz basis. The same can be done for Sy, and I write the calculation in the next page. as before, now that we have the coefficients, the entries of our matrix A, B, C, and D, we're ready to write it down the SY matrix representation. So this is our matrix representation for the operator SY in the SZ basis. Thanks for watching. Bye for now.